a number divides a product of prime numbers, then it must divide one of those primes. I will write that out.
Well, they're allowed to be the same as the prime number. Oh, okay.
Whoa, it's late. Okay. Whoa, how is it late? Whoa.
It's very late.
Whoa. Good. Good. Prime. Okay, so here we go. The prime, and then we'll do something else. So the prime divisibility property. Prime divisibility property says, let P be prime. It says, if P divides a product, if P divides a product of a bunch of numbers, then it divides at least one of them. That's what I'm saying. So if P divides like A1, A2, etc., a product of a bunch of numbers, then P divides AI for some I. Okay, so this is a property that the prime numbers have, and the idea is, I guess, well, what is the idea? Being prime, if P divides the product of a whole bunch of numbers, then like one of those numbers has to have a P in it. You can't get the P is not going to come from like the product of some of them. For example, let's just show how this is not true for like a non-prime number like 4. Armis, bad idea. Okay, so like for example, if 4 divides, I don't know, 6 times 10, does it?
Yes.
It does. Can I conclude from this that 4 divides 6 or 4 divides 10? Clearly not. Okay? Yet, with prime numbers, like if 3 divides 6 times 10, then it just has to be that 3 divides 6 or 3 divides 10. Because, like, where's the 3 going to come from, man? It has to come from, like, one of those numbers, right? It's got to be hiding one. Okay, good. All right, the proof of this, very low level. Have I prepared for this? Sort of. Okay, so there are 2 cases. The trickiest case is the case when there are only 2 numbers. Okay, so case 1. Case 1 is n equals 2. If n equals 2, that's another way of saying, then the theorem that we need to prove is that if P divides A1, A2, then P divides A1 or P divides A2. Everyone clear what I mean by case n equals 2? Okay. Well, this is what I need to show somehow. All right. Well, we do it by cases. Suppose that P divides A1. All right. So if P, so either P divides A1 or not, right? If P divides A1, then we're done. Right? Then we're done. So let's now deal with what happens if P does not divide A1, and we're going to have to show that it divides A2, right? Okay, so instead, suppose that P does not divide A1. Okay, what is therefore the GCD of P and A1 then? Just 1, right? Because P is a prime, so P's only divisors are 1 and itself, and P does not divide A1, so we can conclude that the GCD of P and A1 is 1. And now we're going to use that theorem from last class, Michael, you wake up, of that I can represent this number as a sum of like a linear combination of those two numbers. So what I now know is that there must exist numbers s and t such that ps plus a1t has to be 1 by like that theorem that says that the GCD of two numbers can be represented as a linear combination of them. Okay, but if this is true, everyone with me? Multiply through by a2. If we multiply through by a2, then we get that a2 is ps a2 plus a1 a2t. Okay. But we now have a we now have basically what we need, right?
Yeah.
Because why?
P divides A1, A2.
Yeah, P divides, remember that P divides A1, A2 by assumption, right? We know that P divides A1, A2, and then it's also clear that P divides this, right? So these are both numbers which P divides. And if P divides this, and P divides this, then P must divide the sum by one of those properties of divisibility. So I'll just say, no, since P clearly divides, is this in camera range? Since P clearly divides P times S times A2, and P divides A1, A2T by the assumption together with another property of divisibility, then we have that P divides their sum, so P must divide A2. Okay, so, everyone good? Alright, so what we have, the prime divisibility property says if P is prime, and we have only two factors, then it's got to divide one of them. Because it either divides the first one, in which case we're done, or if it doesn't divide the first one, then their GCD is 1, and then we concluded that it divides the second one. Cool? Alright, so, what?
That's like the whole proof.
That's basically the whole proof, yeah, because now, what if the case 2 is that n is greater than 2? And now, what do we say? Oh, so by this I mean, what we now need to show is, if, again, we need to show that if P divides A1, A2, etc., all the way up to AN, then P divides AI for some I. This is what we have to show, this is what we have to show now. But now we sort of like use case 1, right? Because again, there are two possibilities. Either P divides, yeah, we just kind of like repeat the process and you keep just peeling one off, right? So basically, if P divides A1, we're done. And on the other hand, if not, if P doesn't divide A1, then what we need to show is we must show that P divides A2, A3, etc., all the way up to AN. But that's just going to be true, right? Because again, why must P divide one of these? Well, it either divides the first one or everything else. And then again, either divides the first one or everything else. And eventually we get down to there being only 2 left, and we'll show that if it doesn't divide, everyone with me? So it's kind of like a whole sort of like casework, right? It's like, okay, well, I think I'm done.
Wait, do you need casework? You can just like have a new number which is equal to like A1 times that, and show that P must divide either A1 or that by case 1.
Yeah, well, like actually just like call this like B2 or something.
Yeah.
Yeah. Okay, yeah. Yeah, what he's saying is just rewrite this as kind of like just like just rewrite this as like B1, B2, where B2 is just the rest of them or something, right? Then it has to be 1, 4, or like something like that. Yeah, that works too. Okay, good. That was fun and awesome. I thought we were gonna have like a whole half an hour left in class.